In this video, we're going to talk about Hilbert spaces. But before we go into Hilbert spaces, let's discuss the key fundamental concepts of inner product and inner product spaces. Because without understanding the concept of inner product and inner product spaces, you'll not be able to understand fully what Hilbert spaces are. So let's start with inner product. What is an inner product? So let E be a linear space. That is, let B be a linear space. The inner product is a map. Let's say this is what we call inner product, that takes the Cartesian product of E to set of real number. Okay, the inner product is a map. You can see that it's taking what? It's taking the Cartesian product of this linear space to set of complex number. That means as this is the domain, this is the codomain. So that means every pair of the elements of a linear space here becomes set of complex number. Okay, such that the inner product is, or we can say the map such that the following conditions are satisfied. So that is, this particular map, is called what? The inner product. Okay, the very first condition of the inner product is 1. It is non-negative. X cross X is greater than or equals to 0. That is the first condition. And the inner product of X is equal to 0. If and only if what? If and only if X is 0. Okay? Now, 2. The second condition is the inner product of X, Y is equal to the complex conjugation of Y, X. This bar means complex, the bar means complex conjugation. What do I mean by complex conjugation? Remember from our definition here, we said that the inner product is a map that takes the pair of the linear space to a set of complex number. So that means that the codomain, like I was explaining the other time, of the inner product is going to be what? A set of complex number. It's going to be a complex number. That is, if we pick any two elements from here and the mapping with this is a map, we're mapping this to a set of complex number. Okay? Now, another one. As we have the lambda of X plus the mu of Y, comma Z, the inner product of the lambda of what? Of X, plus the mu of Y, comma, you can separate this as this. This one can be separated as this. Let me split this out. Lambda X, comma, because Z is common, then plus mu Y, comma, Z. Okay? So this one will be what? It will now be eventually lambda X, comma, Z, plus mu Y, comma, Z. So that is, so the pair, that's right. The pair so the pair from here now, E together with the inner product, is called an inner product space. This is called an inner product space. Okay? So this combination is called an inner product space. Alright? Now, let's look at some examples of inner product spaces. So, just as a form of recap, we have defined a function, and I told you that this is a function that maps the pair of this, we call this linear space, to a set of complex number. And before it could be this particular function, before it could be called an inner product, these three conditions must be satisfied. So the pair of that linear space together with this inner product is called inner product space. I believe we still understand the concept of inner linear space. Linear space is the same thing as what? Vector space. And elements of linear spaces are vectors. Okay? So let's look at examples of inner product spaces. Let's quickly look at examples. Examples of linear product spaces. Okay, I think I should clean this. Let's clean this. Examples of inner product spaces. Examples of inner product spaces. Okay, we start with what? The first one. Let's use Rn. Rn is what? Euclidean space, n-dimensional set of real numbers. So this is a very good example of inner product space. That is, if we have have a map, such that Rn cross Rn, goes to a set of complex number, is defined by, suppose we are defining it by x comma y is equal to, summation of xi, yi moves from 1 to n, because the dimension of this space is what? Is finite. So where x is equal to x1, x2 to xn, and y is equal to y1, y2, yn. So the combination of n's, Rn together with the inner product space, the inner product is what? Is an inner product space. Okay? Alright, IPS. Briefly. So this is a very good example of, you can see the way I've defined my concept here. And don't forget what this one simply means. It means that you multiply what? X1, Y1 plus X2, Y2 plus till you get to Xn, Yn. Alright, so that is that about that. That's the first example of inner product space. You could equally have, n-dimensional set of complex number. It's also a very good example of inner product spaces. So this one will change to this. We have this, we are going to have this too. All right, then it becomes this. Okay, in that case, let's say that suppose we use UW, and this case then we have what? Let's say we have ZI W high. So I move from 1 to n. I will write the generic representation for you now, so you understand what I'm talking about. Okay. Now, so let me put my bar here because it will go to set of complex number. All right. So now I is from 1 to n, like I've shown you. So where arbitrary u, where arbitrary value u is equal to, what I use there, I use z1 to z2 to zn, and my w, the arbitrary value of w is what? So w1, w2 to wn. These are in what? A Cn, that is what? N-dimensional set of complex number. That is the dimension of this particular space is n, and they are all complex numbers. So this is another good example of, so that means Cn, that is a dimensional set of complex number, together with what? Together with this inner product space is inner product space. Okay, so let's look at idea number 3. Shall we give more examples? Let's give more example. Another example, this number 2 and this number 3. Another example is the linear space L2. What is L2? The linear space L2. I've explained this to us before. This is a sequence space. A what? A sequence space. It has what? But if I want to write any element in this space now, so suppose I say that x is in L2. So I will write this as this. Generically, I will say x1, x2 till that, because it's a sequence. Okay? If I pick y also in that space as another element here, I will have what? y1, y2, and so on. Okay? So now, if we want to equip this space with inner products, that means that we need what? Inner product of this now. L2 cross L2 goes to what? Set of complex number. Okay? So now, how do we show? Let's say, like I've given us x and y. So we define this. This will be defined by the inner product of x over y is equal to summation xi yi bar I move from 1 to infinity. Okay, that's how that was defined. So that means the combination of what L2 together with this this inner product is an example of inner product space. You observe I use I moving from 1 to infinity because it's a sequence space. This is a set of it's a sequence space, convergent sequences. So it's a space of convergent sequences, L2 space. It's different from the what? It's different from what? The big L, where you have measurable space. Lebesgue measurable space. Okay? So let's look at another example. Let's look at another example so that we'll be able to understand this concept very well. Now, another example here, example 4, is the linear space. Can you still remember this? Wow, do you still remember this? What is this space about? This space is what? A space of what? Continuous, complex valued functions on the, what? Bounded interval 0, 1. Elements in this space are functions. Okay, so let's look at how this is defined. I can say that suppose we have f and g from this space. F and g are functions. And how do we define the space? This is defined by, the space is defined by, the inner product of f and g is equal to the integral, okay, running from 1 to 0, because the limit is between 0 and 1. It's a bounded interval. So f of t, g of t, but you put a bar on g of t just to demarcate that they are not, the same functions. This will be a complex conjugate, and this will be just now, like we have talked about the when we started with the definition of inner product. We are able to say that the inner product, is a bilinear function. Yes, it's a bilinear function. That is, it is linear in one, for example, now it's linear in one, what do you call it? One plane, and the other plane now, and the other, segment, it is complex. Okay, so the linearity is here, and this is the complex aspect of it. Okay, yeah. So now let's look at another one. So that means that this C of that is what did I say? It's a space of complex continuous valued function, or continuous complex valued function, or whichever way we want to call it. So together with what? Together with the inner product. So this forms what we call what? Inner product space, and it's defined by this. So that's this is the definition. All right. Now let's look at another one. The linear space L2, which is between the interval 0, t. T here is a unit what? It's a unit interval, okay? And which has the norm 1. The norm of t is 1. It's just like a what? A compact, what do you call it? A compact interval. Very good. A compact one. So this one, if I pick elements F and G coming from this space, and take notes, this is not a sequential space, it's a space of measurable functions over the interval 0, t. So where you have this to be 0, 1, this is 0, t. So just define it with this way. It's the same thing. The only difference is just that this is like a Lebesgue measurable function, and it's different from the other one because t is a compact interval. The point is compact, so this is close and bounded, and the norm of t is 1. So if I pick any two functions, from this, in this space, I will define it this way. So 0t, f of t, g of t. Then you put bar here. Okay? That is, I have told you what this implies. This is complex conjugate of g of t. And so that means I told you inner product is bilinear. In one segment, that is in one aspect of it, it is linear, and the other one, it is complex. Okay? So I wouldn't want this video to be too long. Let's quickly look at basic properties of inner product spaces. They have some properties. The basic one that we should know. Let's quickly look at them. Let's look at them. Now, basic properties of inner product spaces. So we observe that an immediate consequence of let's look at, for example, let's say for arbitrary elements x, y, z in a linear space E, and let's not forget, I failed to mention this, the lambda and the mu that we use there, they are, you should know that they are complex numbers. So the inner product of z multiply lambda x plus mu y. How do you write this? Good. Now you see that it's like z is multiplying these two linear maps from the left. Okay, we have written this like this. Okay, we could have written it like this. Sorry, let me write it away. We could have written it like this. Sorry. No, we could have written it like this. But because we want to place this particular lambda, we want to bring it to the left. If we will separate this, it will be z, inner product of z lambda x plus inner product of z, we multiply them out from the left. But ideally, we can write like this. We put the bar on this particular lambda, here's z x. That solves the problem. Plus the same thing here, because if I expand this, I will have z multiplying this. Let me write it in the way you understand what I'm saying. So you understand. What I'm saying is this. If we open this inner product, this could be what? It could be z lambda x plus, because you are, it's just as if we are multiplying, you are expanding. Z, z is common. Then mu y. So ideally, this is elementary. Now we want to bring the complex number, this scalar, the lambda and the mu to the left. So lambda bar, you have transferred it to the left, you have to put bar there. It's now a complex conjugate of lambda. Okay? Plus the mu, another what? Another complex number, z y. That is that. So you can also have this z, Another way of representing this is you can have it this way by putting what? Lambda x plus mu y. Let me show you this. And put bar. Yes, you can put bar. You can see that. Look at this ideology. We have transposed. You know, we have transposed the position. You have swapped. This one comes here now. This one goes to the right. This one. So the one that's coming to the left here, put a bar on it. It's a bar. That's complex conjugate. Okay. It will not cover Z. You know, just like the way we have done for this. So you want to bring all of them, all this one to this left. You put the bar on it. So which is going to be, so if you expand this now, you have the bar on, you know, x, z. You are wondering, why did I put this on? I will explain to you. The bar will cover that. Yes. Now compare this one with this one. I said the bar is now on top of everything. Why do you put bar? Fine. You know, here the complex number lambda has a bar here and write zx. So now if you want to transpose it now in such a way that this zx will also have bar, that means x will come here. You know, the moment you are interchanging, when you move from the left to the right, the elements here will have bar, just like we did for the other one. So that's why. So if the x now comes here and z comes here now, so the bar will cover all them, so that because you already are having these complex, and this scalar is already having a bar. So by the time you transpose there, everything will have bar. That's just the logic, okay? So why coming here is to make this on to have bar with z. That's it. So which you can, you can split this. You can separate this as this. You can separate this as this. Yes. Plus the bar of mu and the bar of y, the inner product of y. That's complex conjugation. So which eventually will give us this. Which eventually will give us this. Eventually it will give us from here. If I want to change this now, you can have what? It goes to bar, that is the bar on the what? On this I think I shouldn't I've not cleaned this. Okay. Sorry about this cleaning. Okay. So if you want to transpose that, the bar will disappear. It will give us back. You can see how we have gotten that back. Okay. Yes. So you can see how we got the initial values that are split out bar for. So let's stop here so that video will not be too long. Hi, I'm Dr. OJ. Do well to click on the notification bell so that each time I upload a video, you'll be daily notified. Click, share, and comment. Like my videos. God bless you. Bye.